Experimental investigation of diffraction caused by opaque and transparent barriers.
Hello everyone. First of all, I would like to thank you for watching this video. This video is about diffraction and how it may happen. I would say that we have heard a lot about wave-particle duality, superposition, and this kind of things, so I'm not going to repeat them again. However, in my opinion, there is a missing point in that subject and the relevant experiments, and that is the refractive index of the medium in contrast with the barriers. In considering the diffraction, we normally assume a wave or a particle encounters an opaque obstacle or aperture in a transparent medium for the visible light, of course, where the refractive index of the barriers is much higher than the medium. So the question is here, how will diffraction pattern distribute if the refractive index of the barriers falls less than the medium? To solve this missing point, I did a series of experiments with transparent and semi-transparent barriers inside different media with high refractive index. And here we are going to consider some of them and those experiments as well, and I hope you enjoyed.
To do these experiments we need some equipment including a metal single slit, a glass single slit, a cuvette, 3 types of diode laser, a convex mirror to enlarge the size of the diffraction pattern. Notably, these experiments will be performed inside different media including air, Aniseed essential oil, Cassia essential oil, and some others as well. Furthermore, these experiments will be performed in 2 steps inside air and also inside a liquid for both opaque single slit and transparent single slit.
In this step we will consider the diffraction pattern which is produced by an opaque single slit. The convex mirror is being used to magnify the size of the diffraction pattern, and as we expected the maximum intensity of the light aligns with the optical axis. In this step we will consider the diffraction pattern while the opaque single slit is immersed in water, and again as we expected the maximum intensity of the light aligns with the optical axis, however the width of the diffraction pattern narrows. In this step we will consider the diffraction pattern produced by an opaque single slit immersed in aniseed essential oil, and expectedly the maximum intensity of the light aligns with the optical axis. Notably, the width of the diffraction pattern is variable in this experiment corresponding to the variable refractive index of the medium, which is Cassia essential oil. However, the maximum intensity of the light still aligns expectedly with the optical axis.
Notably, the central band in the far-field pattern caused by an opaque barrier corresponds to the maximum intensity of light independent of the state of matter of the medium. Furthermore, since the refractive index of transparent media which tends to fall less than the refractive index of opaque materials, thus there is no chance to consider such an effect if the refractive index of the transparent medium for visible light is higher than the refractive index of the opaque barriers.
As a solution to consider the effect of the higher refractive index of the transparent medium for the visible light comparing the refractive index of the barriers, I used different types of transparent barriers including glass, borosilicate, sapphire, fused quartz, and transparent soft plastic. In this step we will consider the diffraction pattern caused by a transparent single slit. Unexpectedly, projecting the laser beam onto the transparent single slit produces an unusual diffraction pattern, and a dark band appears at the zeroth order position coinciding with the optical axis. This behavior cannot be explained using Huygens' principle. Moreover, the Fraunhofer and Fresnel-Kirchhoff diffraction equations are no longer valid in this scenario. The convex mirror is being used to magnify the size of the diffraction pattern, and also a convex mirror with a shorter focal length can be employed to achieve higher magnification. In this step we consider the diffraction pattern caused by transparent single slit immersed in water. The central strip remains dark, same as the similar experiment in the air. However, the diffraction pattern is narrower due to the higher refractive index of the medium.
To consider the effect of refractive index on diffraction, we may repeat similar experiments with other organic compounds and oil with higher refractive index, such as glycerol, Himalayan cedarwood essential oil, Aniseed essential oil, benzyl benzoate, and Cassia essential oil. The values of the refractive index of some of oil are invariant to switching from red to blue light, and also in response to a temperature variation. Therefore, as for the glass single-slit experiment inside those media, the diffraction pattern changed rapidly. At times, the central bright band on the optical axis was observed, whereas the dark fringe was observed at other times. The variation was more pronounced at shorter wavelengths, and repositioning the laser beam caused the pattern to shuffle. However, it gradually settles into a steady state after about some minutes.
Diffraction pattern by a glass single slit inside Himalayan cedarwood essential oil. Diffraction pattern by a glass single slit inside Aniseed essential oil. Diffraction pattern by a glass single slit inside Cassia essential oil. If the width of the transparent single slit is inconstant, then we may see the effect of both refractive index and the physical dimension of the single slit on diffraction when it is immersed in a medium with higher refractive index. Therefore, we see here a dark band on the lower part and a bright band on the upper part of the central strip aligned with the optical axis even after the diffraction pattern settles into a steady state.
Notably, the central band in the far-field pattern caused by the transparent barrier does not always correspond to the maximum intensity of light. Conversely, the form of the diffraction pattern are determined significantly by the factors such as the refractive index of the barrier, the refractive index of the medium, the physical dimensions including both the thickness of the transparent barriers and the width of the aperture. Furthermore, the refractive index of the barrier and the medium may correspond to the temperature of the lab.
In summary, considering the results presented herein along with the relevant published article, demonstrate clearly that the refractive index contrast between the aperture material and the immersion medium is a dominant factor in determining the spatial distribution of the single-slit diffraction patterns. Moreover, by considering the diffraction pattern caused by the transparent aperture inside the media with a higher refractive index in contrast with the barriers, it can be inferred that the spatial distribution of the opaque diffraction aperture and correspondingly the central band appears different depending on whether a barrier is employed relevantly to the refractive index of the medium as well.